Hello student, good morning. I am Dr.A.K, Professor of Chemistry. Today I am going to discuss ionization of acids and bases. Last class I have discussed concept of acids and bases, means Arrhenius concept of acid, Brown-Stead-Lowry concept of acids and bases, and Lewis acids and bases. Also I discussed some problems. Now I am going to discuss ionization of acids and bases. Arrhenius concept of acids and bases becomes useful in case of ionization of acids. Ionization of acids and bases, as mostly ionization in chemical and biological system occur in aqueous medium. Strong acids like perchloric acid. Perchloric acid means HClO4. Okay. Hydrochloric acid. Hydrobromic acid means HBr. Hydroiodic acid like HI. Nitric acid HNO3 and sulfuric acid H2SO4 are termed strong. These acids are called strong. Again I am telling you, perchloric acid HClO4. Hydrochloric acid means HCl. Hydrobromic acid HBr. Hydroiodic acid HI. Nitric acid means HNO3 and sulfuric acid H2SO4 are termed strong because they are almost completely dissociated into their constituent ions in an aqueous medium, thereby acting as proton donor, means H plus donor. Similarly, strong bases like lithium hydroxide LiOH, sodium hydroxide NaOH, potassium hydroxide KOH, cesium hydroxide CHOH, and barium hydroxide BaOH2 are almost completely dissociated into ions in an aqueous medium, giving hydroxyl ions. According to Arrhenius concept, they are strong acids and bases. What I told, the name of bases: lithium hydroxide, potassium hydroxide, cesium hydroxide, barium hydroxide, sodium hydroxide, potassium hydroxide, all are strong bases. Alternatively, we can tell the strength of an acid or base may also be gauged in terms of Brown-Stead-Lowry concept of acid and bases, wherein a strong acid means a good proton donor. Already last class I discussed. Then here, according to Brown-Stead-Lowry concept of acid and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. On this concept also, Brown-Stead-Lowry concept also, we can tell a strong bases and a strong acid. Now example I am telling you, acid base dissociation equilibrium of a weak acid. Now we are telling you the acid base dissociation equilibrium of a weak acid. Weak acid means HA, you can tell, capital H, capital A, HA in general. Then HA in aqueous, when it will react with H2O liquid, it will form H3O, hydronium ion, plus A minus, that is the aqueous. Then here according to last class what I discussed, Ha plus H2O, acid plus water, water means always you think H plus OH minus. Then acid means Ha in general plus water, it will give H3O plus, that is a conjugate acid. Okay, conjugate acid is because H2O has accepted H. Okay, then H2O accepted H and it formed hydronium ion. Then this is called conjugate acid, because here H2O is functioning as a base. H2O can function as a acid as well as base, big acid and big base. Then now Ha is the acid and H2O is a base, big base. Then acid base, when both will react, then it will form here H3O plus means conjugate acid, and this Ha acid will now it will convert to A minus. Okay, anion A minus, that is a conjugate base, because H of Ha now used up with H2O and now only A is remaining. That's why it will give A minus, that is the conjugate base. Acid will become base and base will become acid. Okay, means conjugate acid, conjugate base. Now again further you just you understand that dissociation equilibrium, already we have studied, I have taught you. Dissociation equilibrium is a dynamic involving a transfer of a proton in forward and reverse direction. Dissociation of equilibrium is a dynamic involving a transfer of proton in forward and reverse direction. Now the question arises that if the equilibrium is dynamic, then with passage of time, which direction is favored? Which direction after some time? What is the driving force behind it? These are the questions. In order to answer this question, we shall deal into the issue of comparing the strength of the two acids or two bases involved in the dissociation equilibrium. Consider the two acids Ha and H3O. H3O is also acid because H plus is there. It can donate H3O. Then that is also behaving as a acid, and Ha is also acid. Okay, consider the two acids Ha and H3O present in the question reaction what I have discussed. Then consider the two acids Ha and H3O present in the this reaction what I have discussed. Acid dissociation equilibrium. Okay, acid dissociation equilibrium. How acid is dissociating. Then acid dissociation equilibrium, we have to see which amongst them is a stronger proton. Out of Ha and H3O, which one is stronger? We have to compare that which amongst them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over the other shall be termed as the stronger acid. Means which one can donate more proton, that is the stronger, and which is less, that is the weak. Okay. Then whichever exceeds its tendency of donating a proton over the other shall be termed as the stronger acid, and the equilibrium will shift in the direction of weaker acid. Okay. As for example, if Ha is a stronger acid, then hydronium ion. If HA is a stronger acid than hydronium ion, then HA will donate protons and not H3O. Which is stronger? They will donate, you can say first they will donate proton and not H3O, and the solution will mainly contains A minus, means anion, and H3O ions, H3O plus ions. A anions means it will be called conjugate base. The equilibrium moves in the direction of formation of weaker acid. Here you see, if a stronger acid is there, then equilibrium moves in the direction of formation of a weaker acid, and weaker base will form. Okay, weaker base, because the stronger acid donates a proton to the stronger base. Okay, a stronger acid donates a proton to the stronger base. Then here H is donating electron, a stronger acid donating electron. Then now who will take this proton? Then it will take H2O. H2O will take. Okay. It follows that as a strong acid dissociates completely in water, the resulting base formed would be very weak. Already yesterday I told last class that acid will form big base. Okay, big base. If acid is strong, then it will form big base. If a base is weak, then it will form a strong acid. Reverse case. Okay. It follows that as a strong acid dissociates completely in water, the resulting base form would be very weak. That is, a strong acid have very weak conjugate bases. Strong acids have very weak conjugate bases. Strong acids like perchloric acid, means HClO4, hydrochloric acid like HCl, hydrobromic acid HBr, hydroiodic acid HI, nitric acid HNO3, and sulfuric acid H2SO4 will give conjugate base ions. Conjugate base ions like ClO4, ClO4 minus, Cl minus, Br minus, I minus, NO3 minus, and HSO4 minus. These are the base which are much weaker bases. Okay, after donating H, what will remain? That is the base and weaker base, because they are formed from the strong acid. Weaker bases than H2O. Similarly, very strong base would give a very weak conjugate acid. On the other hand, a weak acid, as for example HA in general, is only partially dissociated. Weak acid, when acid is big, then obviously it will donate less HA, because acid is big. A weak acid, say HA, is only partially dissociated in aqueous medium, and thus the solution mainly contains undissociated HA, because weak acid is less dissociated, very less. They will be mostly undissociated. Okay, undissociated, very less it will be dissociated. HA is big acid I am talking about. Big acid, say HA, is only partially dissociated in aqueous medium, and thus the solution mainly contains undissociated HA molecules. Typical weak acid are the example of weak acid I am telling you typical weak acids. Then here nitrous acid means HNO2, hydrofluoric acid HF hydrofluoric acid, acetic acid means CH3COOH. These are the weak acid. They will dissociate very less it will dissociate. Most of them will be undissociated. It should be noted that the weak acids have very strong conjugate bases. Reverse way I told you, acid is there, it will form base, means conjugate base. That conjugate will be strong. Reverse case, acid is strong, then conjugate base will be weak, and if acid is weak, then base form means conjugate base will be strong. Okay, like that way it will apply for base also. A strong base will give weak acid, means conjugate acid will be weak, and weak acid will give a strong base. Okay, this don't forget. Then here I told you weak acids have very strong conjugate bases. For example, NH2 minus, amide I am talking about, NH2 minus, O2 minus and H minus hydride ion are very good proton acceptors and thus much stronger bases than H2O, because they are a strong acceptor. Strong, you can say hydrogen acceptor, are very proton acceptors and thus much stronger bases than H2O. Certain water soluble organic compounds like phenolphthalein indicator, phenolphthalein and bromothymol, this is also indicator, bromothymol blue behave as a weak acid. Both are weak. Phenolphthalein and bromothymol blue behave as a weak acid and exhibit different color in their acid and conjugate base. Okay, conjugate base forms. These two, phenolphthalein and bromothymol blue, behave as a weak acids and exhibit different color in their acid. Shortcut you can tell HIN. Ion means indicator. Capital H, HIN, and conjugate base IN minus. Only IN minus. Both have different color. Okay, HIN aqueous, as for example acid, weak acid, phenolphthalein and bromothymol blue. HIN, it will react with water and it will give HIN, it will lose the H, only IN it will give, means base, conjugate base. Okay, and it will be color, blue color B. Okay, and this H will be taken by H2O and it will form H3O aqueous conjugate acid. Then this HIN, actually HIN means acid indicator color is A and different color. Okay, and other color that indicate this indicator will give, after reaction with water, it will give another, you can say that will give you base, conjugate base, and another color it will give. Okay, such compounds are useful as indicators in acid base titration and finding out HIN concentration. Okay, then this I have told you about the these things, ionization of acid and bases. Acid and base, they are ionizing and they will maintain equilibrium. That's why you are studying here acid and bases. Now another term is there, the ionization constant of water and its ionic product. Ionization constant of water and its ionic product. This is also based on equilibrium. Some substances like water are unique in their ability of acting both as an acid and a base. We have seen, I already given example, we have seen in case of water, in presence of an acid, in presence of an acid, it accepts a proton and acts as the base. Means acid and water. Acid in general way Ha, it accepts a proton and acts as the base, while in the presence of a base, means B minus, it acts as an acid by donating a proton. Already we have discussed. In pure water, one H2O molecule donate proton and act as an acid, and another water molecule accepts a proton and act as a base in the same time. See, if two molecules you are taking H2O, then one will function as a acid, other will function as a base. This is a very, very important thing. In pure water, one H2O molecule donates proton, means acts as an acid. Another water molecules accept a proton and act as a base at the same time. Okay, then you can write equation like this: reaction H2O plus H2O, H2O plus H2O. You will think there will be no reaction, but it is not like that. Both are liquid. H2OL, H2OL plus H2OL means liquid. One is functioning as a acid, other is functioning as a base. Then it will form H3O conjugate acid, and other will form OH conjugate base. Then this conjugate, because acid after losing hydrogen, it is forming OH, the strong base, conjugate base. And another they are taking another H2O is functioning as a base. It is taking hydrogen and it is forming hydronium ion, then conjugate acid. Okay. Then for this reaction, H2O plus H2O, and it is giving H3O plus OH minus. Then for this reaction, what will be the, you can say, K value? Dissociation constant. Here K will be called dissociation constant, because here we are considering dissociation. Then the dissociation constant, how you can write? Then products, concentration of products divided by concentration of reactant. Then here we can write concentration of products means H3O plus into OH minus, means molar concentration of H3O plus into molar concentration of OH minus divided by molar concentration of H2O, correct? Then this is the K, this is called K. The concentration of water is omitted. The concentration of water is omitted from the denominator, as water is a pure liquid and its concentration remain constant. H2O, denominator we are writing now, that concentration, product of concentration divided by reactant. Then in down, we need not required to write, you can say, H2O concentration. Why? Because water is pure liquid and its concentration remains constant, hence not required to write. Okay, down. Hence H2O is incorporated within the equilibrium constant, or simply you can tell K is equal to molar concentration of H3O plus into molar concentration of OH minus divided by H2O is there. Then a cross multiplication you do. Then K into H2O. K into H2O. That is, they will give a one constant. That is called ionic product of water, Kw. Kw means K into H2O means denominator into K, because H2 is already constant and K is also constant. Then a new constant, that is called Kw. Then Kw is equal to H plus and OH minus. That is called ionic product of water. Okay, ionic product of water. Simply H2O you have taken. H2O, it will ionize like H plus OH minus. Then K will write, how will you write K? The K will write concentration of H ion into concentration of OH ion divided by H2O. Then K into H2O, cross multiplication, K into H2O, pure water. Then it will give a new constant, Kw. Kw is equal to molar concentration of H ion into molar concentration of OH ion. This is called ionic product of water. The concentration of H ion has been found out experimentally. What is the value of concentration of H ion? Experimentally it is found, and its value is 1 into 10 to the power minus 7 m at 298 Kelvin. 1.0 you can tell, 1.0 into 10 to the power minus 7, that is the molar concentration of hydrogen ion at 298 Kelvin. And as dissociation of water produces equal number of H and OH ions, that also you know that number of H ion and OH ion will be equal. Then obviously when H ion concentration is 10 to the power minus 7, 1 into 10 to the power minus 7, then obviously OH ion concentration will be the same, means 1 into 10 to the power minus 7. Then means you can tell molar concentration of OH ion is equal to molar concentration of H ion, that is equal to 1.0 into 10 to the power minus 7 at 298 Kelvin. Okay, then what will be the value of Kw? Then now put the value of H ion and OH ion. Then Kw will be 10 to the power minus 7 into 10 to the power minus 7. Means 1 into 10 to the power minus 7. Okay, into 1 into 10 to the power minus 7 means a square. Then 10 to the power minus 7 into 10 to the power minus 7. It will be 10 to the power minus 14, and 1 into 1 again 1 only. Hence you can tell Kw is equal to 1 into 10 to the power minus 14 m square. This is the value of Kw. The value of Kw is a temperature dependent. Here again you should know the value of Kw is temperature dependent, as it is an equilibrium constant. Kw is a temperature dependent as it is an equilibrium constant. Then because it is in a constant you have calculated, then equilibrium can say depends upon the temperature. Then here if temperature is more, that what you have written value 10 to the power minus 7 into 10 to the power minus 7, that is the, I can say at 298. If temperature will change, then this value will change. Keep in mind. The density of pure water is 1000 gram per liter. Again, don't forget. Okay, very important things. The density of pure water is 1000 gram per liter, and its molar mass is 18 gram per mole, H2O. 2 plus 16, 18. Molecular mass is 16. That's why 16 gram is the means 1 mole. 1 mole. Okay. 16 plus 2, 18 gram is equal to 1 mole. 2 plus 16, 18 gram is equal to 1 mole. The density of pure water is 1000 gram per liter mass. Okay. And molar mass is 18 gram per mole. Means 1 mole means 18 gram. Then how many moles are present in 1 liter? How many moles are present in 1 liter water? Then divide it. 1000 divided by 18. 18 gram means 1 mole. Then 1000 gram means how many moles? Then 1000 divided by 18. From this, the molarity of pure water can be given as 55.55 m, because 1000 divided by 18 gram. Okay, because density is 1000 per liter. Then 1000 gram per liter, and this 18 gram divided by 1000 gram per liter per mole divided by 18 gram. Then you will get 55.55 m, capital M, molarity. Therefore, the ratio of dissociated water, the ratio of dissociated water to that of undissociated water can be given as, means dissociated and undissociated. Undissociated is more, dissociated is less. Then what is the ratio? Means dissociated water mole and divided by undissociated. What is the ratio? Then easily we can calculate that 10 to the power minus 7, that is the dissociated. 10 to the power minus 7 divided by 55.55. Okay. This we have to divide, because undissociated is 55.5 molarity, its concentration, and dissociated is 10 to the power minus 7. Then 10 to the power 9 minus 7 divided by 55.55. That is equal to 1.8 into 10 to the power 9. After dividing, result will come 1.8 into 10 to the power minus 9. Or you can tell roughly 2 in 10 to the power 9. Okay. Then this value exact is the 1.8 into 10 to the power minus 9, or roughly you can tell 2 into 10 to the power 9. Then this is this equilibrium, or you can tell thus equilibrium lies mainly towards undissociated water. If this is in equilibrium, H2O, H plus and OH minus, then here, because undissociated is more, hence equilibrium direction is towards undissociated, because dissociation is very, very less. Okay. Then this value is very less, 10 to the power minus 1.8, or you can tell roughly 2 into 10 to the power minus 9 is very less. Thus equilibrium lies mainly towards undissociated water. Okay. We can distinguish acid, neutral and basic aqueous solution by relative values of H3O and OH concentration. On the basis of H3O this H3O plus and OH concentration, we can tell acidic, neutral and basic, which is acidic solution, which is neutral and which is the basic. Acidic, basic and neutral we can distinguish according to the concentration of hydronium ion and hydroxyl ion, OH ion. Then if H3O is greater than OH, then it will be acidic. If H3O, H plus is already attached, with H2O. Then H3O, hydronium ion, if H3O plus is greater than OH, then it will be acidic. If both are equal, H3O plus equal to OH minus, both are equal, hydronium ion and hydroxyl ion, then it will be neutral. And again, if hydronium ion is less than OH ion, hydronium ion is less than OH ion, then it will be basic. H3O means H plus is attached, that is the less than OH. OH means base, always you keep in mind. Then if H3O is less than OH, then solution will be basic. Okay, that I have told you about the pH, not pH, this about the, I told about the ionization constant of water or its ionic product. Okay, this important some value I told you, that is asked in examination also, and in solving the problem or numerical, these are used. Okay, today I am stopping only here. Again we will discuss next class, we will discuss pH scale. Okay, thank you.